Hey everyone, I'm Fiona. I'm here with John, who we took a class together at UC Santa Cruz with Larry Polanski. And it was kind of an interesting experience, that class, because you were coming into this composition class as an engineering major. So can you kind of introduce yourself?
Oh, yes. I'm a John. I'm a graduate from UC Irvine Biomedical Engineering, and I took courses at UC Santa Cruz for several reasons, but I needed to supplement my coursework at UCI. I wasn't taking courses there. UC Irvine was gracious enough to allow me to finish my degree at other UCs. There are some rules there. So I've worked in UC Davis's wheat genetics lab. I was in a tissue lab for a little bit at UCI. And so I've taken a lot of coursework, and it got to the point where the syllabuses, if you line them up, some of the courses would have been the same. And so I had to kind of venture out just to get the credits and the technical electives and things to graduate. So I ventured out, and UC Santa Cruz is very interesting because I did not know this, but they are really heavy into music theory. And what was the Malaysian, the bell? You walk on campus and you hear the bells, right? What was that?
Oh, the gamelan. Yeah.
Yes. Yeah, it's crazy. And in the evening, like you hear this music always going, and it was wild. It was great. So Dr. Larry Polanski was gracious enough to allow this random undergraduate guy to kind of wander in and take his course. He didn't have to. I've gotten weird looks before. I remember trying, or he would have let me, like there was a plasma physics, upper division plasma physics professor who was going to let me take his course as well, but I moved. And so, yeah, Dr. Larry Polanski, he took me in. He didn't have to. And all I had was what my background, what I brought. And it was a very positive collaboration. And I appreciate his patience with me. I was a third string trumpet player in the marching band in high school. Like I was not good. I was terrible. I was a terrible trumpet player, and he had patience, and he in the class helped me along with this stuff. But but the thing about Dr. Larry Polanski was he had his bachelor's in mathematics and he had his PhD in music. And so at heart, at his core, he was a mathematician. And I would watch this man. He would go through the notes and the fractions in his head like this, and he would break down the music and I marveled at this as he would go through and how he designed the music. And if you looked at his notes when he was a student, when he was a graduate student, or during his studies, you would see pages, and it would be anything from like a German choir to very diverse music. He would look and he would circle 3 notes. Mm-hmm. And he was so focused on this. And if you look at his old notes, he approached music almost like a mixture of a scientist and art, and the detail. And so just him circling these 3 notes, and then the notes that emphasizing on it, why the composer would do this. And I marveled at that. And I can't count fractions like he can, but I learned his mathematic approach to music, and I've emulated that during that class. And my approach to music, because I'm a terrible trumpet player, I'm terrible, but I can emulate what I see, and I try to emulate with his music theory what he was trying to do. And he was the one that was trying to kind of align music design with nature. And of course, the most basic rule that all nature follows is math. And that's kind of what motivated the meeting today.
Right. Yeah. No, Larry was really big into like just intonation, Pythagorean tuning, and also microtonal music. So where you're kind of really experimenting with the different ratios and the different distances of the notes from one another in a particular scale. But yeah, that stuff was, I think back then it was like way over my head. Like I was still kind of like, I'm all about equal temperament, but then equal temperament's not really ever seen in nature. It's kind of a man-made thing where we divide, your octave into 12 equal parts.
There's actually like a meme. Everything's a meme nowadays, and it's like a one panel comic. And there's one thing where it calls order and chaos,
Mm.
and it shows chaos. There's a have you seen this with the pine leaves? Maybe I should where it takes like a pine leaf, and it shows the needles of a pine, and it shows order, and it shows a natural flow of how the pine needles go, and
Mhm.
then it shows chaos, and it shows the needles taken apart and stacked, and it shows kind of like the inverse of how we think, where we see order, but our order is actually chaos compared to the natural law, and the natural law is actually order, but we see it as chaos, but it's not. And that's I'm going to pull that up.
Okay, yeah, yeah, please.
Are you let's see, so are you able to watch this? So it's a pine, I'll share in 1 second. Pine needle, if I just go pine needle chaos and go share, boom. All right, great. So on the left here, you see this is order, and then this is chaos, and this is exactly, I think, what you're trying to capture. This is it right here, where you have nature is order, and
Mhm.
you see the flow here. There's a lot of information built here. Obviously, the distribution of these pine needles are for nutrients, sunlight, and it's built with time and death. This was a living thing that is trying to survive, and this is the optimal distribution of it. And to us, this looks like madness, but it's actually order. Versus on the over here, you can see my mouse moves like
Yeah.
this.
Uh-huh.
Cool. So this is chaos. To us, this is order,
I
but this
know.
is actually chaos. And but it looks nice to us. So what does that mean? Is we're wired to understand this, and this is how a lot of musicians, when they approach music, you'll have really good guitarists that can, go ding ding, hit all the notes, boom boom boom, boom 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 boom, right?
Right.
But this is us interpreting nature, and it's not correct. And the same thing with music and flow is actually here. It's actually here. What we should be, all artists should be focused on is this. And so you brought to me, I can't pronounce the word, Fibonacci series, right?
Fibonacci series, yeah.
Fibonacci series, yes. Fibonacci series. And of course it arises in nature. And I watched some YouTube videos, some basics of it. And I remember it from my college days as like just a series, a sequence in a series of adding stuff together, and the next set, iterative, all that. But it captures a distribution and a flow to it. And so what your motivation that you kind of see, it's out there. I think this image captures it, where musicians are here, but they need to be here. And it's an inverse. It's counterintuitive to what you think. It's the opposite. And
Mm.
so how do you invert your brain? How do you think differently? How do you go from thinking like this to kind of the flow of things? And you'll get better music.
Right.
The music on the radio today, I know that you'll I took an art history class, and I got it wrong. I remember during the final, the professor, it was a junior college, and he read and he's like, "You didn't learn anything in this class." Because I was talking about art is in the eye of the beholder, and it's relative. There's no good art, there's no bad art. I gave this thing, and then his argument was there is good art, there is bad art. And I think with the music nowadays, I've heard stuff where they have it down where they can, this may sound controversial, I don't want to, this may offend people,
It's-
but I'll go ahead and say it. So like a Yogurtland, I have 3 kids, and everything is yummy at Yogurtland. Like, we go there and we're like, yeah, Yogurtland, they get whatever toppings, whatever, it's all great, right? And that's kind of the music that you hear over the radio that they designed, and they have advanced algorithms, and they reduce things down to basic chords that and I heard at one point it was like the same group that was developing a lot of the music, from Katy Perry to Lady Gaga. It was the same algorithm of developing music, where it's just simple stuff, but people, it's like yogurt land. It's like in your core, like, oh, this is I can drive in my commute to my car. It's
Right.
nothing substantial. It's nothing immersive. It's going to scratch the surface of my interest of my brain, and it's going to it'll suffice. I'll tap my feet. Yeah, there's a beat to it, but I'm not going to be immersed in the music.
Right.
And that's what producers do nowadays, that you hear over the radio. And of course, it's all funneled in where it's kind of I was telling this to my daughter, like, you won't hear really good music over the radio. You have to find the good music nowadays. You have to research and find it, because it's out there, but it'll never make it to the surface. Unfortunately, that's just the industry. And it's all yogurt land. You go there, and I can just go chocolate. Just make a big chocolate thing and just eat gummy bears, right? It's all yummy. It's nothing more than that. It's empty calories. It's almost it's a waste, but it's background music at, I have a bounce house. The kids, they jump in the bounce house. It's just music you put while they're jumping in the bounce house. It's not going to do anything, but it's designed that way. And they found a simple chords, simple using biology, where you have the rhythm of the natural rhythms, and things that exist in the brain, and they tune into that, and they design and develop around that. And when we take it at that level, it's like you can superficially entertain and it will work, but anything more immersive, you're not going to get it. To get something more immersive where someone stops, and the whole thing, like when you're writing a good joke, comedy's tough. A good joke, a good story, something that is good. The person normally in life, they go through their day, everyone's busy, and everyone's having, especially nowadays, having a hard time. They'll go from A to B. So they'll go to the store, they'll go to work, but if you can make someone stop and turn their head, what is this? You did something. And that's rare. You did something. Music nowadays doesn't do that like it used to. People would hear a new sound and go, what is that new sound? And they would turn. Same thing for art, same thing for I hope for a good movie to come out. Every like 5 years, a good movie will come out. People don't go to theaters anymore, but a movie will come out in theaters, and you have to go see it, because it's just, like Usual Suspects, right? The plot twist and good writing. It's hard to find good writing. It's hard to find good music. It's easy to write a book. Anybody can write a book, write a good book. And as you go through all this different media, it's very tough to find something as the audience that stops them in their tracks, and they don't even realize initially what they're watching, and they kind of turn and they look, or they stop and they go, what is this? And they take it in, and then you hit something. You hit a primal chord in that person, and that's value, and that's very tough. That's very tough to find. Very tough to find. I think all musicians are looking for that. And what this is here is the best, most simplistic representation of that. That's what when a music, I want to call it like a music developer, they're always looking for a new sound. They're looking for something. They're looking for their style. You can master an instrument. Okay, cool. You can functionally master an instrument. You can play an instrument. Now make music. Completely different. There's a big difference between playing an instrument and then writing for an instrument. And so when you propose your questions to me, it was about linking the order of nature to writing music. And you brought up a sequence of function that describes that nicely. And it's very, very, it's simple, but it's very complex. And past week it's been very frustrating, but it's very complex, but it's beautiful. And there's other functions in nature like that. There's other patterns that occur that you can base creating, designing something. And what you're trying to do is what electrical engineers are trying to do. It's what Wall Street's trying to do. Microtransactions. I know New Jersey, they have a bunch of guys and they have microtransactions, and they have algorithms and softwares, and it gets more and more complex. They have scientists, that PhD guys, or guys that are really good at fluid mechanics, that could be working on rocket design. Instead, the fluid flow, they're working, and they take their math over and they're working in right by the waterfront, New Jersey, and they're working on microtransactions to make more money. So with the markets, and it's a rabbit hole, it's infinite, it goes in forever. So what you're doing with your music design, what you want to do is exactly what they're doing. They're doing it for money. You're doing it to create and make music. And it's very difficult. And when you want to develop an algorithm, that's what they do, algorithms. When you want to develop an algorithm or a process for that, you're now wrestling nature, and that's a fight. That's a fight, because a lot of stuff in nature hasn't been, what's the right word, conquered, hasn't been understood yet. If you get deep in these math books, they'll tell you that beyond the scope of this book, or not, not covered in this book, or they'll do a lot of assumptions. Those they call them conditions. And so when you see like a very complex math problem, they'll put at the end of it, they'll put footnotes and conditions. And what that means is they don't understand, but so they understand, they'll put these footnotes, these conditions, and in this scenario, it works. But when you apply it to the real world, it doesn't work. So what does that mean? Well, they'll say, we understand, this is a pine tree, Christmas tree. We understand like the pine tree here. Oh yeah, this is my finger, I'll use the mouse here. We understand the Christmas tree here, but really what they're doing is this, right? And so what algorithm designers, electrical engineers, Wall Street, Goldman Sachs, they're basing billions of dollars of assets, and they're looking at this, but they're modeling it like this.
Wow.
But it's really this. And so you touched at the core of a lot of issues and that affects all industries with your question, your proposal. And so you want, how do you inverse and switch your brain? And what tools in nature, like the sequence you provided, could you use to go from thinking like this to like this? And this is order and this is chaos. And you introduced, now I apologize for my crudeness here. Let's see here. So you introduced this guy here. Okay. So you have this sequence and series, and you look at this, and right away, you look up here, 0 plus 1 equals 1. 1 plus 1 equals 2. 1 plus 2 equals 3. You go, this is simple. And so you can look at this and go, all right, this is pretty easy, right? I got this. And then you start looking at, all right, well, what's the output of this? And I see a 1 here, a 1 here, 1 here, 1 here, 2 here, 3 here, 5 here, sure, 13, 21, 34. Cool. See a nice spiral here. Cool. All right, I get it. But it's always deceiving, right? It's not what you think. For example, what I mean by that, it's once you have a solution that you can easily explain, everyone gets it. But meanwhile, for thousands of years, you had very smart people looking at the sky, and they didn't understand how it worked. And it was a simple transformation of, don't base how the sun travels and all the planets kind of follow like this. Don't base it on a circle, base it on an ellipse. So instead of a circle, an ellipse. And if you do that, then you can now actually map out what's going on here, because as things stretch out, you can see now it's moving like an ellipse, not a circle, but like an ellipse. And so when you do that translation, it makes sense. And everyone said, oh yeah, of course that makes sense. But no one saw it for thousands and thousands of years. This is the similar type of problem. And a lot of this stuff occurs in nature. And so right away, when I saw this sequence of series, before you even get to And the music side of it, I'll take 10 minutes here, 45, to discuss like this pattern here. And if you look at, we'll go to, there's a Wikipedia Cantor set here. So the importance of 1/3, this is the Cantor set. And it looks simple. It's mind-blowing. The whole universe is based on this simple. It's called Cantor. I think I screenshot the Wikipedia. Finite composition. The Cantor set. There you go. Cantor set. So that's what this is here. It's a summation here. There you go. And it's really based on this. It's 1/3. 1/3. So when you analyze sequence and series, a couple things will stand out. You can ask traditional math guys or that study these things, guys that do what do you call it? What's the cryptologists and encryption guys and these things, and they utilize transformations and matrices and things like this. And one thing that always pops up is this number here, 1/3. 1/3. 1/3 is very interesting. So if you have, I don't have a reference for this, but basic engineering, if you like pedaling a bike, if you look at to get max power and efficiency, it's a curve. So imagine a nice parabola, right?
Mhm.
It's going to be here to get peak power, to get peak performance, peak output. It's 1/3. So 1/3 is, imagine. So this is more for like the listeners that they hear this. If you look a basic, guy, what's the most optimal way when you pedal a bicycle, and if you're looking at these charts with output power, the answer is 1/3. So that's a quick, that's a reference just to this. So 1/3 comes up in nature a lot. The Cantor set, this is 1/3 here. And you go, where does 1/3 come from? Basically, you can YouTube everything here. I haven't reviewed this in probably 10 years. The Cantor set, I just pulled it up right now. But if you look at here, right, and here, so you have 1, this bar equals 1. And then 1/3 is removed here, right? And then you're left with 2/3. See the black bars here? So this here, there's a bar here, that 1/3, ready? Removed. That's 1/3. That's where you get the 1/3 from. 1/3 is removed, 1/3, 1/3, and this goes on forever. And so just like the sequence you pulled up, where there's a lot of reoccurring themes behind it, the Cantor set is one of those that has a lot of properties and also examples in nature. And there's some things that for example, one good way, I don't know if it's been postulated, I don't know if they're there yet, but maybe your listeners can look at it. So if you have a black hole, for example, based on the Cantor set model of energy distribution, 1/3 is going to be involved. So what does that mean is a bunch of mass comes in, energy comes in, and then X-rays are spit out. You're going to have a 1/3 function somewhere in there, transformation occurring, how things are stripped down to, subatomic quarks or photons or whatever, X-rays, from matter going in into what's being expelled. 1/3 will be present because it's based on the Cantor set. So that's one thing that pops up in nature. I just want to emphasize the importance of 1/3. That's important. The next thing would be, we have the concept of a circle, right? Everything you see is a circle. We live in a circle universe. You can't escape it. Every classical physics problem, right? It's always a circle. The sun, the moon, you look up, it's a circle. Why? Because gravity spins everything around, makes the planet circle just by brute force. Gravity and the nuclear explosions going on in the sun. What's equilibrium? It's a circle. Everything's a circle. So we live in a circle universe. It's governed by the circle, the number pi. So now, pi comes up. where's my thing here? So we have pi now. So this is an anomaly here, pi. You know, it comes up in nature just like your sequence, just like the Cantor set. Another thing that comes up is prime numbers. I'm not that good at writing it out, so I'll just type it. Prime numbers. Greatest mathematician would be able to find a way to relate these two numbers together, pi and prime. So prime number occurrence, if you look at it, they can't, they don't know how prime numbers, and they build bigger and bigger and bigger and bigger computers, and they're trying to figure out like a general formula just to calculate prime, where you plug it in, you know, with variables, you plug it in and you can predict prime number occurrence. They can't do that. A good mathematician will be able to relate pi to prime. Maybe one day. It's very difficult, very complex problem that stretches across. You would see, you know, computer architecture greatly increase and all this stuff. Society would be better if you could solve this problem. So that's another sequence and series, right? And then if you deal with the series that you presented, this guy here, right away you look at this and go, all right, 55, 34, 21, 13, 85, you know, and you look at this, and people that deal with these issues, they don't like odd numbers. They don't like odd numbers. I'm sorry, I got that backwards. They don't like even numbers. Even numbers are a dead end to them. Even numbers are a dead end when they're analyzing this. Dead end, right? This, they can't understand that they just build big computers, like Japan, the United States are building bigger and bigger computers trying to like solve this pi. They can't. This here, whoever analyzes this, they use the same computers and they're trying to calculate more and more. And if you even mention an even number, they're like, get out of the room, get out of here. We don't care about even numbers. But the problem is here you deal with even numbers, and this is beautiful. So if you were to look at this here, let me see where this guy here, how can we do this? We can go UCRI, maybe a Microsoft Paint Master. So this is a nice curve here. Cool. Yeah, there's enough time for this introduction here. All right, I'll shake this down here. Let's see. Cool. Here. All right. And so where's my, I made a note. All right, so just bear with me here. This will be worth it. I should have had this prepared for you. I did it by hand, but I should have had it prepared for you. So this will help your musicians. And so you see this here. It's like, I see this, and when I see curves, I go, okay, you're dealing with curves. Do I take this curve and do I do a transformation? Imagine a sphere and a ball, right? And do I take this, there's a function here. Do I take this function and do I wrap around a sphere? Do I take this function, do I wrap around a football and make it elliptical? Like, what do I do with this function here? There's obviously a curve. Are there other things involved? Imagine a z-axis like shooting straight down. I can do this here. So imagine like, right, I shoot straight down, right? Is this thing being stretched out like this, kind of like the sun? And like, what's going on here? Is there another function behind driving all this? So when I look at this curve, I see all these questions pop up. And what's really going on here? Is it something simple, this or that? I don't know. But just a simple approach, maybe one of your listeners can find, is right away. These hash marks are not going to be to scale. I'll just do this really quick right now. Do big hash marks here, bigger. So these numbers here, there's a 1, 1, 5, 8, 13, 21. So let's go. All right, we'll go like 1. Oh, it's gonna be bad. I apologize. I should have had this already done. One here. We'll go 5. Not to scale, of course. We add it up here. And we'll go 13, right? And then we stretch out to 20. There's 21 here, right? and then we'll continue to go here. What else we got here? We got a 34. All right, sure. 34. And then, yeah. And we go here, 55. Sure. Maybe more, right? 55 there. All right. So all we did was we take these constants here, these numbers, and that's how we're going to treat them. That's what we have here. All we did was just uncoil this and just map it out. Cool. All right, great. Now the next thing we do is we take this here. We look for correlations. We look for relations. And so basic stuff here. I like that word pretentious. That's what this is. So okay, we'll do iterative sets. Move this guy here so I have more room here. Yeah, this is cool. And so the same hash marks here we'll make. Let's go here, 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 here. I'll take okay, and we start making another set. And so we'll do a summation. A summation here. That's the summation. So this is simple here. This is just the series that you pointed out. 1, 1, 2, 3, 5, 8, 13, 21, and 34. 55 would be over here, stretched out. So this is a series stretched out here. And if you look in red, and then down here, we have a separate line. And that's enough for now. This line here would be a key, which maps this line here. And I'll share screens in a second here to go back. But in a sense, it's the concept of a recursive pattern. And the summation, because there's another function in the background acting on it, it's not one-to-one. And so what that means is when you look at the image, which I'll show in a second here, this is actually more representative. And you find a pattern here. It goes from 12, 8, 20. This number here is 12. This is 20, 33, 54, and 88. This other one down here is 108. And there's a transformation here of 1/3. And that's important. And as you take this line here, this is a function here. This is the series here. So the math behind it, there's a basic equation, just like the Cantor set, where you can write it where it's really nice like this. There is the Wikipedia. You can look up the definition of the series here. So that's what this is here. And there is another function that's acting on it, that's going on in the background. That's what this is here. And I think that this function here, and I'll write out what it correlates to. So 12, 20. So this one here, 1, 1, 2, 3, 5, 8, 13, 21. This is important for the math guys out there, so they can see this and they can go backwards. Let me really quick take 2 minutes to type this out.
Okay, yeah, no rush.
Cool.
Yeah, my band practice was canceled at 4 o'clock, so it's perfect.
Really?
Yeah, it's all good.
Oh, I remember are you still playing? I watched you rocking out on stage. That was cool.
Oh yeah.
What was it called? The Psychic Birds, or right?
Close. Telepathic Birds.
Telepathic Birds. Yeah. Cool.
Yeah, so it's all good. Take your time.
Do you watch Coast to Coast or no?
No.
Or listen to, what Coast to Coast is?
No. What is it?
George Norrie?
No.
Okay. It paranormal stuff.
Oh, okay.
Let's see. When you do so much in the direction of science and engineering, you get not bored of it, but like you need something else. the opposite of it, just to kind of like wind the mind down in that direction. And so you look to like the paranormal, and it almost like relaxes the brain so you can jump back into. And so you find yourself like going between engineering and the paranormal, just as like as just like a kid would go from, not to be so condescending, schoolwork to like cartoons.
Oh yeah,
You,
yeah.
you don't want to go home and watch like cartoons, right? So you know what's, it'd be faster if I just write it out.
Okay.
This is going to be a 13, and where I'm pulling these numbers are from here, directly from this image. And this signifies this like continues out here.
Right.
This is 34, and I'll stop here, 34. So because there's another function back here working in the background is tough to identify, what that function does to this when you're dealing with this is it turns this into, let's see, it's keyed to 12. This is 12, and this is the end result. So you put it through a function, and this will be the end result of that function. You have this as the input. Imagine a machine, a box. You crank, you turn, and this is the output that it would produce. So you have 12, and your math fans will appreciate this. You have 12 on this segment. You have 20. Same lines starting. I have to start at 5. So 5 here. So starting here. It's clear. There. So starting at 5, when we go right here, when you put it through a function, it's going to equal this. It's going to equal 12. How do you get 12 from this? 1 plus 1 plus, let's see, 5 and 3 is 8. 8, 9, 10, 11, 12. Okay, there's your 12. The next thing is and then you can go on, you go 20 here. Okay, this is just a simple summation here. Actually, I'll write this up here. The interesting thing was this. That's nothing. And then we go 33. We're just adding this, right?
Right.
So as we do a transformation here on this line equals 33. But what it really, this is the part that I think your guys would appreciate. And then you start looking for patterns. And if you take this, so this is, if you take 8, zoom in. So now we define this. That's tough. Okay, so 1, 1. So we know that 1 plus 1 plus 2 plus this here, this block here equals 12. It equals 12.
Mm-hmm.
So, all right, that's fine. This teardrop shape equals 12. Cool. This here equals 8. So if we go 12 minus, this is sequence and series. This is like analysis. If we go 12 minus 8, we get 4. So what does that mean? 12 minus 8 equals 4. That the rest of this function views this as views it as 12. And so this becomes 12 here. So now 12 and 13. So now 12 and 13. And here's another function here. And so what this becomes is 4, 12, 36, 108. So this is actually not 12. 12 is actually 4 under this this is another function. This is the key we care about, this line here. So this here is actually viewed as 4. 4 plus 8. We have our 8 here. We have our 8. This here, sure, it adds up to 12, but because it's projected relative to this 13, this is not 12. It's actually 4 relative to this 8. So 8 plus 4 is 12. And now we have 12 and 13. And 12 and 13, and we deal with that 21. And we put those into this machine, this function to go from here to here, to go from this line to this line. We crank it again, we get 4. This one is to this line where 8 is, we get 12. And then from this line here, we get 108. I'm sorry, 36. 36 would be here. And then 108 will be here. And you go, how do you go from this nice spiral series of 1, 1, 2, 3, 5, 8, 13, 21, 34 to 4, 12, 36, 108? And the answer is, well, there's transformation functions in the background. So we have this. This is just a simple sequence summation here. And now we have this other line established here where we're adding 1 plus 1 is 2 plus 3. This section here is 12. This is 8. Based on this is 8. Well, 12 plus 8 is 20. And then 8 plus 13. And we can start building this all the way down. So 20, this is 33. This is 54. You guys actually want to go through and do all the addition, 54, 88. These numbers will pop up. And it's the translation transformation where you go 8 plus 12, 8 plus 12 is 20. 8 plus 12 is 20. 13 and I guess 13 and 20. So 13 and 20 is going to equal 33. So right, 20 plus 13 equals 33. 21, and you continue this pattern here. So what I'm drawing out the graphical representation of a mathematical function, which you can represent with a simple series, just like this guy here. But it's so you can, where is it? That's all I'm doing here. I'm just writing out a simple sequence here graphically, so you can understand it. And you see a pattern here. Okay, that's fine. And that's just adding. The thing is when you deal with this function here, and I want to get the spiral again. Let's see, where can I, let's do this here. Oh, Cantor set here. Fibonacci sequence. Cool. Images. And so we have this nice, this template here. And this, you can write, this goes on forever. You can write like 10,000, the number here. The pattern's the same. So I'll copy this image here. And so what are we really doing? It's a simple concept of this, that you have this here. And that there's a relevance here where this here is 1 plus 1 is 2. Okay, let's go. 5 plus 3 is, or 2 plus 3 is 5. This is 10, 11, 12. So, oh, yeah, John, I add this up as 12. Who cares? Well, the rest of this cares. You see this teardrop shape here? This is a teardrop shape here. Mm-hmm. If you look, you have like a teardrop trailer, right? If you're going out, here's a teardrop trailer here. Here's one, right? Let's look at the next one. Here's another teardrop trailer here, right? Like a snail. All right, cool. Here's a bigger teardrop trailer here, right? That set. Here's another one here. And here's another one here. So in this picture here, this set, we'll stop at 55. So we have really one complete set. Boom, done. 1. Now 2. That's in its own. 3, 4, 5, 6. So you have 6 of these you have 6 snails living in this box, right? And because of that, like, who cares? Well, okay, sure. 2 plus 3 is 5. 5 plus 5 is 10, and then 12. 12 and 8. Who cares, John? The other snails care, because relative to that, because this thing's telescoping, this one here is not 12, it's 4. When you respect to this guy. So if snail, we'll just say if this snail here looks at this, it doesn't see it as 12. It sees it as 4. And then 8 and then 4 plus 8, you're going to get 12. So now that makes more sense. You have 12. You actually have 12 here. You don't have 8. You don't have 20. You have 12. And so you write literally here. All I'll write it here, here. You have 12. So it doesn't see 12 here. It doesn't see this as 12. It sees this as 4. And then 4 and 8, and you have 12. Same thing here. Now we can blow this up to the next one, and you have 21 here. You have 12 and you have 13. Okay. Well, it's not going to, 21 is not going to view this as 12. Let me see. This 8 and 13, 21, 12. 21, 4 plus 8. I apologize. 76. We can calculate this again. So this is the whole fundamental form of the function. So this is not 12, this is 4, this is 8, and it's all derived by 1/3. So 4, so this adds up to 8, but this snail here, it'll view this as 4, which is 1/3 of the 12. And so just using simply 1/3, how would 21 view the summation of this, knowing this is 4, 12. So we have 4 plus 8, that's 4 is 12, and we have 13. We can add that together, and we can look at 1/3, and then we can start projecting this out. And this pattern just exists throughout. Which is the original here. So it actually should be right here. 4, 12, 36, 108. So this one here is 4. This block here is 4. This block here becomes 12. This becomes 36. So that being said, let's see, is that right? This is 36 here. And what you end up seeing here is there's a function that's built around 1/3 in this sequence, and it's relative, and that is what describes this guy here. So these numbers are key, and this is me just doing like the math like by hand. 4, 12, 36, 108. When you apply this function here, this is what you get. And what powers this function here is a transformation that's powered around 1/3. And so I took a long-winded explanation just for us to get back to the concept of 1/3 and how important it is. And so the fact that 13 would see this 12 as 4 shows that there's a function involved in the background, and there's a transformation there. What does that mean? Well, that function here explains something like this. That function there is related to the same concept here of a telescoping series, a geometric telescoping series of 1/3. And if someone, that's why I reached out, if someone could map this out, what I projected here, it's a simple puzzle game, like a really, basic Sudoku, maybe with a little twist. If they could just look at this and say, all right, well, this is 4 relative to this. 1/3 of 12 is 4 here. This little guy here is 4 instead of 12, 1 plus 1. And then, all right, now fill the rest of the puzzle. How would that 13 here would see this not as 12, but as 4. Okay, well, how would 21 view this section right here? This section right here? How would 34 now view this section here? Because you're telescoping down. Relative to it, what would it be? And there are patterns there, and there's numbers there. And I started messing around with it a little bit, and what immediately kind of came to me was prime numbers, and there may be some pi there. So when I said, like, I need another month to like really play with this, I think that your listeners, they may find if they just look at that pattern here, what I wrote out here, they may find the functions here, these transform functions here. This is really important. That actually relates to, prime numbers or pi. With the motivation, because 1/3 popped up while doing this, right when you see 1/3, you always go to Cantor set here, Cantor set, and when that pops up, people think now you're looking at infinite expansion because that pops up. Now look at a sphere, look at three-dimensional objects projecting upon, and people who search prime numbers like United States, Japan, right, and they just study prime numbers, they hate even numbers. They don't care about even numbers and prime numbers. If you have 88, if you have 54, they'll tell you get out of the room. They don't want to hear it because prime numbers. But here it's interesting, when you look at these sets, you have even numbers, but the correlation between these even numbers is 1/3. And there's a relationship there where you have even numbers and they do this dance with 1/3. 1/3 obviously is, you deal with the Cantor set, and also 1/3 it introduces, now you're talking about the realm of prime numbers. And then maybe playing around with pi and prime numbers back and forth, you may be able to solve the function here of this that's driving behind this series that you presented. There's something there. I'm not good enough to look at it in a week, but there's something there. But the whole point of all this was to say that function would be a great tool to use for music development, music theory, whatever that function may be. And that function would be in line because it's natural distribution. It would have, energy flowing through it. It would have natural distribution. It would be able to mimic order pretty well. It would be a good function to design music off of. And that was one of the things that you said, is look at this series, and this series would do it. Before this, I would say to try to capture nature, I would say, I know you do a lot of cool stuff. And so before you presented this, I was going to initially talk about, like, all right, so I listened to the stuff that you got and the frequencies. And I'd say, you know what, take like a metal sphere, right? And a metal ball. And of course, size would matter, but just whatever, metal ball. And if you hit it on top, the frequencies, they would travel, and you would get a different frequency as the energy as it traveled through the sphere, and you get a different frequency, and you can kind of map that out. There's a function there that you could look at if you're looking for a sound, and just has the flow of the energy. You hit a circle, right, and it travels through. You can capture just different line segments, and this is something that you can do in your home if you're trying to develop something. It's like, all right, what does the music of a sphere sound like? It's like, well, take a sphere, metal ball, and hit it, and then as the sound travels through, record it. It's gonna be even distribution. Then time it, and then take slices and segments of the time as it travels through, and then you can develop music based on just that flow alone. This series is more powerful than that because this would be like inclusive in everything. I'm not good enough to map this out to pi or prime numbers, but there's something there that's worth investigating. Maybe that's why I initially said maybe one of your listeners can really dissect this and dive into this sequence and series. But there's something, I know when there's something there. I know there's information, and there's something there. So that's just an example how I would approach this for a function to develop music around. If I know that, like, if you're making guitar pedals or something like this, guys can kind of add resistors, and they can do things to get a noise or a sound. For your purposes, if you wanted to use math, I would find shapes that you could obtain,
Mhm.
and using UC Santa Cruz as motivation, as the sound travels through those shapes. If you hit it, um, and then analyzing that, and then using that to devise music would be another approach. Just the spacing of it, there's information there as well. Um, so the to answer your question, that was the approach I was going to take initially, and then you presented this to me, this puzzle and riddle, and it's occupied me for a week now. Um, for a week, so like, 30 beers later, like, this is where I'm at here, and there's something there. It would take more time, and I almost want to take, and I brought up a sphere. I want to take this here, and I want to either put it on a cylinder. I want to take this function and wrap it around a sphere or a shape, or telescope it out, to see relatively how 13 would view the summation of 12 next to 8, and actually see what's going on here, because there's some spatial component, spatial temporal component that I think is going on, that's not captured. Uh, you're looking at a shadow.
Right.
This is a shadow of something way more complex. You're just looking at a shadow, and you're saying, all right, describe Fiona with here's a shadow of her going like this, holding something. Now describe Fiona. It's like, and you're holding a box. You're like, well, but if you understood the function, you could say, no, this is Fiona. She's holding a box. This is just a projection, of something, and those components. I'm not good enough to figure it out in a week, but maybe one of your listeners can. But
Mhm.
there's a projection there where the numbers are relative to each other, and if they can add those parameters, those rules, those components, maybe they can find a general rule that
Mhm.
describes how the numbers, each sequence would seat relative to each other. But there's patterns there. It involves 1/3. Another one that came up when I was messing around with it, 1/5. And right away, Dr. Larry Polanski, with his notes, as he would go through those fractions in his head, 1/3, 1/5. And I remember doing this stuff. I'm like, I wish he was right here, because I throw numbers at him and he would just solve them. So when they look at this, the take home message with this series, the examples illustrated, try to find the functions, and then the transformations. Use 1/3, 1/5 popped up. That may be irrelevant, but definitely 1/3. That's all I have to say about this series. And if you can find that function,
Mhm.
um, I mean, that opens up a lot of doors. You could definitely design music around that. If you can't find that function, how would I use this? Well, functionally, you have a sequence. If you can't master that function behind this, you have another sequence and series. There's a lot of sequence and series in nature. Then now, all right, we're taking a step back. Generally, how would you use a sequence and series in nature to make music? And right away, I would say, go to a swap meet, throw away the math for now.
Mhm.
Just take a step back, go to a swap meet, go to an antique store, find something, record it, hit it, measure the frequencies as sound travels through. And that is the impulse response of energy traveling through a ball, a sphere, do
Mhm.
different shapes. And if you want to make a song based on shapes, a sphere, that's a great start. There's going to be a pattern there. There's going to be a flow to it. And that would be, if you want to, you could do a whole catalog, a whole album discography based on how you interpret sound transfer, a wave going through a sphere, a wave going, you get a triangle, I'm sorry, pyramid, how we'll go through that. And that in itself will be another natural system as energy input as it travels through. And then taking quantitative measurements of that, seeing the distribution, and then basing music on that. That'd be another one. I remember you and I, we were talking during break, and you told me the stuff you did, and oil was a good one. For example, oil and water, because you said that you were utilizing images or you're trying to capture analog and digital, and an oil dispersion in water will be good of that, where you're not that good, no one's that good, where, all right, hey, draw in 10 seconds, draw an oil drop. I'm sorry, in 10,000 pictures, draw an oil drop dispersing through water. You would have an idea in your head, right? But it wouldn't be accurate. Instead, let nature take the course, right? Going back here, don't try to do this. You know, you're not going to be able to do this. No one's that good. You're gonna take this and you're going to turn it into this. So instead, all right, let the plant grow. Watch the plant grow. See how it grows. You can model something based off that, because nature's better than you at this. It has to be. And for oil and water, or food coloring and water, lava lamps, for example, that's an analog signal, and that is nature flowing. And computers, they say they can, but they can't accurately, something like that, like a double, you can look up double pendulums, they can't. So when it comes to heavy lifting like that, let nature do the work, record, and then base your work, your interpretation of that log of how nature responded, and then generate your music based on that. And that would sum up my approach, based on Dr. Larry Polanski's in the classes, the teaching on how to approach music with music design. That's the approach I would take. So it all comes down to order versus chaos. And musicians, just to kind of wrap up everything here, musicians nowadays, they see chaos and they have it wrong. That's they're ordering their interpretation of nature. Nature is the true order. Their interpretation is chaos. And try to get clever with transformations, using the math, the matrices. There's a lot of programs out there that can help you, and generate your own. Like these guitarists, right? Like I don't know much about it, but there's like foot pedals, right? And guitarists, they'll have their coveted foot pedal. You're a so these things, right? And they'll go to their guy that makes the guitar pedal because he makes that one, and it's unique. The guitar pedal, it's unique. And so when you can use these basic tools in mathematics to make your own custom proprietary guitar pedal that no one else has, so you can have your computer function that generates music, or it's a toolbox. It's a tool in your toolbox. You open it up and it can generate a sound you're looking for, and you can grow your music sheet. You can grow your music based off that sound, or a couple sounds, utilizing that quote foot pedal. And I believe that's what you're ultimately looking for is, John, I want a guitar foot pedal, but I want a way to make foot pedals, a logical approach to making foot pedals to produce the sound. And using these kind of math functions would be a way for that. And then once you find something that's key to you that you like, then that's gold. Then you can run with it. I can toss you, not you, you not play the guitar. You could toss me Jimi Hendrix guitar, and I couldn't do anything with it. Like, go, no, it's his guitar. He did it. And it's like, I can't do anything with it. I was a terrible trumpet player. But you toss it in the man's hands, he starts jamming on it. And so you have to find, with these functions, these algorithms, a guitar, an algorithm you can jam with. And so what works for somebody else is not going to work for you. And how do you find your algorithm that you can jam with? That's just you. You're going to hear something, it's going to click, and it's going to say, that's it. Kind of like how I talked initially, how something that will turn your head, it's going to turn your head. And if it turns your head, if you take that tool and you utilize it, and you make a new sound, new music, then you're going to turn other people's heads, because now you're jamming. Now you're Jimi Hendrix jamming on the guitar, and people are turning their heads. So that's what you're looking for. And that's some very basic, I'll say that word, pretentious ways that a musician can utilize just a logic and a thought process on how you can find your guitar pedal to start rocking out on your algorithm. And I know there's a guy in the National Guard. He's a cool guy. He makes he calls it trap music. And I looked at him, I'm like, oh, is that Fruity Loops? Because I remember Fruity Loops from like the early 2000s, you know.
Right.
And he's like, sort of, and he's doing all this stuff here. He's mixing, you know, but he has his rhythm to how he does that. And if you can utilize, I would say, the math just to, like Larry Polanski did, he circled, I remember he would always emphasize like 3 notes. He would have the sheet music, and he would see a group of notes, and he would just circle it. And it was like, why would the composer do that there, that there, right there in that measure? Why? And so this is really, when you get down to the applications of it, it's about you developing the timing and the notes that you would put in a measure, and just circling it. And then basing things around that, utilizing these tools that math could provide for you. So that's really the motivation of it. Yeah, Dr. Larry Polanski's notes, and taking just a simple sound, breaking it down in notes, in a measure, and then literally building movements based off that.
Yeah, no, this is very fascinating. And I feel like there's so much here that many composers have not tapped into at all. Like, because I mean, I know composers that have used systems to, like, what is it called? Process music, they'll limit themselves to certain things, but this is way more than that.
There's tools. If I know, like the keyboards and the software, it's so limited, and you were more hands-on, because I heard some of the sounds that you were making. And if you go outside, just go to a swap meet, and really try to, you don't have to break down the math and the equations and the charts and the growth and these things. It'd be this way for you. Yeah, you don't have to. Just literally go and just make a recording. Grab a metal object and hit it. Record the sounds, and look for those frequencies that you like, and then build something based off that. There's no keyboard that's going to so there's no synthesizer that can make that sound. And what's the filter in that case? I know the paper I submitted, you talked about filters. Well, you're the best filter. You're the best filter for you. You're Jimi Hendrix in the guitar, and you're jamming. And so there's you have to find a sound, and you can use a algorithm approach, or you can use a more, I say, what they would call chaos, but I actually call ordered approach, is using real live media to do that. But yeah, a lot of people rely on Fruity Loops, and they have, if you look at Katy Perry, Lady Gaga, they have researchers just studying how to feed people Yogurtland. And it's good, but it's not a master of the craft. It's not
right.
It's not, you're not going to be immersed in it. It's not going to turn your head. You're just going to sit there in the elevator and kind of like tap your head in the lobby. You're in the lobby, tapping your foot, and that's it. Yeah.
Right. It's like fast food music.
Yes. That's what it is. Yes. By design. Yeah.
Yeah.
The simplest, and that's what fast food is. It's an optimizing. It's let's cut down the expense. Let's cut down and let's just serve a product that gets the job done. And that's what the music industry is now. You can't afford to have mastery. It's easier to churn this out than to have something that is I'm trying to think of like a really good, like unique flavored ice cream at Yogurtland. You say, where did this come from? Yeah, it's all been water. It's all watered down and just reduced down to a gelatinous mass, if you will, the radio. Yeah.
Right. No, this was very informative. And I feel like we could definitely elaborate more. I'm kind of curious, maybe in the next podcast where we could maybe, and maybe this would be my own research of like how this could be applied to like a composition, like harmonically, how could this be applied rhythmically in a piece of music, melodically, and then also like I know composers that use absolute time points, and I do this too. I use like prime number time points. So at like 3 minutes in, a certain event happens. But I'm kind of curious how to organize the material leading up to that point, because the way nature does it versus the way people do it is very kind of unpredictable.
If you had prime numbers on a piece of paper, and imagine like a ruler or a slide rule, like a ruler. Now this ruler is a function, and if you lay out the prime numbers, and then you go, all right, I see the prime numbers. I want to do my timing, my rhythm based, and I'm going to base my movements and my measures on the prime numbers in general. But what if you had a ruler that was a function and you overlay it? And now instead of basing off of prime numbers, this function, it's prime number relations is built into it. And now you're basing stuff as you move this along the prime numbers. There's another pattern there. And that is another tool that you could use instead of just going off prime numbers. And that's what that series presented with the other stuff behind it. There's way more information here.
Right.
There's way more information here as you go down. So instead of going off the top line, well, do the transformation, find the function, and then go off the third line here. It's key to 4, 12, 36, 108. Okay, now let's apply 1/8 to that. Okay, now how does that relate to other sequence and series? And that's going to develop a natural pattern because it's built in. That natural pattern, I want to use that as a motivation to write this. It's going to be, I'm going to use this set of numbers now that I developed utilizing this Fibonacci series.
Yeah.
And after I put it through a transformation, this function, I'm now going to write my music based off this set of numbers. So that would be how you would apply that. And that's the artist, how they can take a sequence, a series, a new set of numbers, rules, natural rules that govern and that's the box that sets the rules, and then they're going to make their piece based on those rules, following that pattern. So you would have to get those functions, those patterns down, and you can explore. And I've been messing with it for a little bit. And like I said, the numbers that pop up with that Fibonacci series is 1/3 and 1/5 pops up a lot as you expand it out, and finding those functions and then basing music off that would be pretty cool to see.
Yeah, and I'm very curious to kind of apply this in the next thing I work on. But yeah, thank you so much, John, for your material and your wisdom and your knowledge and your research. It'd be definitely cool to do a part 2, down the road. I think there's just a lot more to say on this. So yeah.
Yes, thank you for having me. And this is more of a plead for more skilled people than I to look into these patterns, and maybe they can formalize a nice function that we all can use in different applications. But I'm pretty good when there's information there. I'll stop and I go, no, there's information. There's more information there. And that one, there's a lot of information there. That's just doing the basic Google searches and YouTube searches on that series, it just wasn't there. So I would like to take that series out. Maybe they could stretch it out. That they could do a transformation. I just want to say, this is like my plug. If they could like transform it on a sphere, transform it on an ellipse, just different shapes. If they could do a transformation on these functions to see elliptical coordinates, if there was something there that made sense, just like the sun, everyone thought it was a circle, turned out to be an elliptical transformation. If there was some kind of projecting transformation function there, I'm not that good. Maybe one of your listeners could be that good. You can get a generalized function that makes sense. You plug in values and makes sense, and then you can, make non-Yogurtland music based off that.
I like that. I
Cool.
like that.
Thank you so
Cool.
much, though.
Yeah, thank you so much, John. If people want to get in touch with you to find your work and stuff, can they do that or
Yeah,
what?
I don't have any I don't have any social media. I fix machines. Um and if they yeah, Jonathan Hately at Gmail is my email. Jonathan JONATHANHATELEY at Gmail. That's my point of contact. I'm not on Facebook. I don't do social media.
It's probably
I
good.
am a we have a I'm a partial owner of this is a shout out 925 Studio Fit off the 4 freeway right by Kinder's, a couple doors down from Kinder's on Arnold. And we do jiu-jitsu, boxing, and fitness. And so my daughter, she does arm bars, she does chokes. She's fought in Vegas twice. I've competed in Vegas twice.
Wow.
I lost. I'm not that good. She's good. I'm terrible. I'm terrible. Like this is from judo throws earlier this
Oh
week.
my
I got
gosh.
like bruises all over all the time. So I care about jiu-jitsu. I do a lot of jiu-jitsu. And my coach is Erico. He's known in the jiu-jitsu community. Yeah, we're over there by the 4 freeway by Kinder's, and I'm always there. And so if anybody wants to do jiu-jitsu, we're over there, 925 Studio Fit, right off the 4. We have like a banner up right by Kinder's.
Awesome.
Like 2 doors down. So
Grab
but
some.
that's I'm in the studio, the dojo, getting beat up by people better than me. That's all I do all day. Yeah.
Awesome, John. Well, it was good talking to you.
Yes, yeah, it was. It was good seeing you again too.
I know. Okay, we'll talk to you later.
Yes, take care.
Okay, bye.
Bye.
To